Well, good afternoon. Welcome to today's webinar, How to Achieve Optimal Melt Control in Cast Iron with OES Analysis. We have a fantastic webinar for everyone today with Kevin Liu of Hitachi High-Tech Analytical Science. Before I introduce him, I want to go over a couple of housekeeping items. First, this webinar will be recorded and made available to today's attendees. You'll receive an email with a link to the recording within a week after the webinar. Second, the presenter will be answering questions at the end of the session. You can type your questions in at any time during the webinar in the question box in your webinar control panel. Now let me introduce our speaker, Kevin. Kevin is an application specialist with Hitachi High-Tech Analytical Science. His current role focuses on the development of customer applications within the technologies of X-ray fluorescence and optical emission spectroscopy. He is passionate in developing solutions for quality analysis and holds an interest in the implementation of Hitachi High-Tech within industrial processes. Kevin, welcome to the group, and the floor is yours.
Hi everybody, and welcome to our webinar today. My name is Kevin Liu, and today we'll be talking about the best practices for melting process control and how to improve your results. But first, let me tell you what this webinar will cover today. One of the biggest problems that foundries face today are the errors that arise within their analysis of materials and the processes implemented to take and collect samples. For foundries that produce cast iron, the analysis of carbon is essential, but difficult due to the formation of excess carbons in either ductile, gray, or compacted graphite cast. The results from analyzing these types of cast often produces wrong results due to the top layer of carbon or graphene impeding the results of their actual material. The goal of this webinar today is to go over the best practices you can implement within your process to produce the best results. So the main talking points we will cover today will be sampling and sample preparation, OES theory, analyzer solutions, mobile versus stationary, as well as sample analysis. As with all quality analysis materials, good sampling and sample preparation plays a key part to minimize error. However, most sources of error occur before the sample is even analyzed. We will go over the best practices to implement within a QA/QC environment to produce the most precise and accurate results. Here we have a graph outlining the relations of good sampling and preparation versus errors in the analysis. It's important for you to understand from here that the most important factors affecting good results from your measurement are good sampling and sample preparation. From a theoretical standpoint, error propagation or propagation of uncertainty is defined as the effect of a variable's uncertainty on the total uncertainty of measurement. For all instruments, there are certain degrees of error associated with your analysis due to limitations such as the precision of your instrument. This error propagates due to uncertainty from other variables such as sample taking or sample measurement. All in all, the main takeaway from this is that error propagation is defined by the root sum of the squares of uncertainty. In other words, meaning the better your sampling and preparation of samples, the better your results will be. In order to produce the best measurements, we must ensure that we minimize error by sampling and preparing samples in the most effective way possible. In order to take the best samples and prepare the best samples, the most important factors to take into account are: 1, timing of sampling. In order to get the most representative measurement of melt, it is very important to allow for your melt to cool down to a temperature where it becomes homogeneous with the rest of the batch. It's important to have a set time that's dependent upon what kind of melt you're working with, allowing for all the samples to homogenize the same within all your samples. 2, high representative status of sampling. This is very important, so you ensure that the samples you take is representative of the whole entire batch. For cast iron, in order to receive the most accurate representative of the batch, you have to avoid all slag and go deep into the melt so you're actually getting the material you need to analyze. 3, tying into homogeneity here. In cases where samples are inhomogeneous, the sample that you take can have drastically different compositions or microstructures than the rest of your batch. 4, it is important to ensure that the samples do not include faults. There should be no inclusion of slag or cracks. And it's also very important to wear visual filters so that you can distinguish between the slag and the melt to prevent slag absorption. 5, sample handling. Handling samples is a very important part of the quality process, so you can minimize outside factors and ensure that the results that you produce are reproducible and precise within all your samples. And the final one is samples measured with spark sources should be conductive and of a certain size so that the complete aperture of the spectrometer leading to the source is covered. We will go more into this, we'll go more in depth with this in later slides where we review OES theory. One of the most important factors with sampling is homogeneity and the avoidance of faults within cast irons. To receive the best cast iron samples, gray solidification within casts must be avoided to achieve the best homogeneity for carbon. In non-ferrous materials, it is very important to avoid segregation within samples with sediments with the use of special molds. To produce homogeneous samples requires a high cooling rate of up to 50 degrees Celsius per second, thermal conductive molds with appropriate material such as copper, clean molds, minimal sample size, ideally around 25 to 30 millimeters, and also an immersion probe used to eliminate faults that can impair with traditional sampling, such as cold shuts due to interrupted sample casting, slag buildup, gray solidification, and complicated sample preparation. Just as important as sampling is sample preparation. To prepare samples of steel, nickel, cobalt, and titanium, the best method to use is to use a grinder. Depending on the material of the analyte or the element of interest, aluminum oxide sandpaper of grit size 40 to 80 is the best to use. With grinding, it is also important to avoid cross-contamination. What this means is that when you're analyzing an alloy with a drastically different composition, say for example, stainless steel and bronze, it's important that you change the grinding paper so that the stainless steel doesn't contaminate the bronze. Samples that are aluminum or copper based would be best prepared by using a lathe or mill. Here we have a video that showcases the proper sample preparation techniques. We will not go over this today, but if you're interested, you can download this and review. Common methods for analysis are optical emission spectroscopy, combustion analysis, and thermal analysis. With OES or optical emission spectroscopy, the pros of using it would be the wide range of elemental analysis, including carbon, as well as light elements. There is a low cost of ownership, and you can produce the fastest results with a relatively low degree of sample prep. Combustion analysis is a technology that limits the analysis of elements to just carbon and sulfur, or nitrogen, oxygen, and hydrogen. There is a high cost in purchase and ownership, as well as a high degree of sample preparation, therefore meaning there's a high operational cost. Thermal analysis is also used only for carbon. It can only analyze carbon. There is a high degree of sample preparation, and like combustion analysis requires new cups per analysis, meaning there's a high operational cost with this as well. Of the three methods, all the three methods can analyze for carbon accurately, but OES provides the fastest and most reliable results at the lowest cost of ownership while maintaining low sample preparation. One of the most popular spectroscopes with an analysis of metals is OES. Today, we will place a strong emphasis on the theory of OES and components that are characteristic within all spectroscopes. So what is spectroscopy? Spectroscopy is essentially the study of light and its respective properties. Different types of spectroscopes operate within different areas of the light spectrum. With OES, this technology operates within the visible and ultraviolet spectrum, operating within 120 to 800 nanometers. So how does OES work? With OES, a spark is generated and passed through an electrode in either a spark or an arc form. From this, the surface of the sample is melted, therefore shortly exciting the electrons to an excited state. The excited electrons emit light as they cool off and return to its original ground state. The light that's emitted by the electrons are then transferred via optical fibers or direct light path to an optical system and then a computer where the data is then processed into a spectrum. Here we have a schematic of the OES process. So to recap from the last slide, a current is generated in the form of a spark that melts the surface of a sample. The light generated from this is fed through fiber optics to the optical system. There, detectors detect the light intensities and provide a readout to the computer, where the results are referenced to a calibration. Here we have the internal optical system. The light feeds into a slit in the upper right-hand corner. From there, the light hits a grating that refracts or splits the light onto CCDs or charge-coupled devices, with each detector covering a certain range on the spectrum dependent on the wavelength of the light that hits it. Intensities measured from the CCDs are then relayed onto a readout system in the computer to generate a spectrum. Doing so produces intensities and wavelengths that correspond to elements of interest, indicating not only what elements are present, but the quantity of elements present. Spectral results from the analyzed material are then referenced to a calibration curve that is calibrated with certified reference materials. The intensity of the elements being measured is now being matched up with a nominal value that's defined by a CRM. By measuring the range of these CRMs, we can reference intensities to composition. For example, a cast iron would operate under an iron-based calibration curve that is calibrated with a large number of CRMs. CRMs are reference materials that come with a certificate that states the uncertainty, reliability, and traceability of what you're analyzing. All CRMs are lab tested and are subjected to many forms of testing. The use of these CRMs is therefore obligatory for accredited testing or calibration labs in QA/QC. Now, when you measure an unknown, the intensities from the spectrum are then relayed to the calibration curve, where results are generated in the form of elemental composition. Analyzer solutions from Hitachi High-Tech. One of the many solutions that are offered are stationary optical emission spectrometers. With stationary OES, there are benchtop models or floor standing models. Generally speaking, the larger the optical system, the more accurate the results you will receive. Some of the benefits are as listed here, with high resolution and analytical performance. Stationary OES has the highest degree of accuracy and precision, provides laboratory-grade results operating through a complete spectral range of 120 to 800 nanometers. Due to this comprehensive range covered, stationary OES is an indispensable part of any metals quality process. In contrast to the large, bulky stationary OES is mobile OES and handheld XRF, or LIBS. These analyzers are the ideal tools for incoming or outgoing verification of raw material scrap, or even NDT of finished products. Mobile OES also offers fast and accurate analysis of many elements undetectable by handheld instrumentation, such as carbon, with the ability to sort gray casts in arc mode. However, mobile OES does not offer the same precision and detection limits as stationary OES due to the smaller optic. So, with sample analysis arises many questions, such as, why does OES need to be analytically checked? What is recalibration? When should I perform a recalibration? How do I correct for deviations within my results? There are many factors that require you to check or recalibrate your instrumentation. As with all types of instruments, components will age over time and not function the same as when they were first manufactured. In terms of OES, the major components that need to be accounted for are the lenses and windows, which will get dirty over time. Therefore, less light gets into the optical system. Environmental factors can also play a role in interference of the flow of argon through a system, as well as component performance. Electrical interferences can also cause the electronics to deteriorate over time. It is important that the analytical system has a means of accounting for this drift. In order to account for this, the spectrometers need to be recalibrated or standardized. To do so requires a 2-point restandardization to bring the spectrometer back into spec. There are two types of errors, additive and multiplicative. Using a 2-point correction method accurately corrects for both a bias created by an additive error as well as a skew created by a multiplicative error. Single-point recalibration methods cannot accurately account for both types of errors. In this image, the low point is corrected by bias and the top point is corrected by skew. These corrections modify the sensitivity of the spectrometer, therefore adjusting the calibration curve performance to match when the instrument was originally calibrated. When should I recalibrate? Recalibration is an important part of every quality process. It is done to ensure that the instrument is providing accurate results that are reliable and precise. Every process is different due to the number of burns performed every day, so it is important to establish within your SOPs the frequency of recalibration should be performed. Recalibrations are often performed after a predefined time interval or after a predefined number of measurements. The last step of the recalibration process is analysis of control samples or standards to check the accuracy of your measurement. Control samples. So all control samples should have a similar composition to the analyzed material. For example, you wouldn't check an aluminum standard with the cast iron. They should also be very homogeneous. They should also have been verified by different testing methodology to confirm accuracy. It is important to use CRMs or certified reference materials as they are lab verified and tested using many analytical methodologies. They should be used for unknown sample verification to test instrument performance and for SPC during quality control. Control samples should be readily available, meaning there are enough samples for you to measure without the need to source more. Measurability, meaning that the sample is large enough to actually analyze. Recently prepared so as to prevent contamination from external factors, such as oxidation. It should also be similar to the sample you'll be measuring. So for all processes, it is important to have a set of defined tolerance levels. The best way to go about doing so is to recalibrate your spectrometer and check the results with CRMs. Then, with the known values of the CRM, define this as a control sample on the database of the spectrometer. To ensure the highest reproducibility, measure the samples 10 times per day on different days with recorded deviations so as to create an acceptable tolerance. Results should be within 2 and 3 sigma of the known value. SPC and quality control charts. So there are many advanced processes that can be implemented with analytical instrumentation to improve overall processes. One of these processes is SPC. Statistical process control is the means to control the production process by identifying the reasons for drift with the objective of improving the production process. Statistical process control is made up of 3 core elements: data collection, determination of the control framework, and reduction of drifts or deviations. Tools such as SPC produces process flow charts, type schedules, histograms, cause and effect diagrams. It can be used to monitor the overall performance of all your instrumentation. So thank you guys for your attention. If there are any questions, I'll pass this off to Shannon.
Thank you very much, Kevin. So as a reminder to all the attendees, if you have a question, go ahead and type it into the Q&A panel within your dashboard, probably on the bottom of your screen or the top of your screen, depending on what kind of browser you have. And while all those are flowing in, we did have a few come in during the presentation, Kevin, so I'll start with those. One person asked, what can OES analyze at low levels of detection in cast iron?
So OES can analyze a wide range of materials. So within cast irons, the most important elements that it can analyze are sulfur, boron, carbon, manganese, chromium, and nickel. And it can even analyze trace and tramp element levels.
Okay, thank you. What is meant when you say recalibration of an OES instrument?
So over time, OES, like all types of instrumentation, will drift from its original set calibration. So an OES instrumentation needs to be standardized on a regular basis to reestablish the original calibration. The only reliable method is to analyze control samples or certified reference materials to bring the analysis back within the spec.
Thank you. Another person asked, do I need to burn longer to measure carbon and iron using like a portable device instrument?
You will need to burn longer. With our iron base, we have a cast iron function, and if we run any samples on it, the cast iron is probably 3 or 4 second longer measurement than any other measurement. So this is to burn through the initial layer of carbon so that you're actually analyzing the material itself.
Okay. How often should you measure your control sample?
So you should measure your control sample periodically so that you can confirm your results. Also, depending upon what you're analyzing, it is if it's an unknown, you can use it to confirm the results of your analysis.
Okay. Do you also use CMOS sensors in your stationary systems?
What was that?
Do you also use CMOS sensors
Um,
in stationary systems?
we don't use CMOS sensors, no.
All right. Anyone else? Go. A few seconds, we'll wait for you.
Yeah.
All right. Well, if you think of any other questions, in the meantime, feel free to respond to the email that we will be sending with the recorded webinar, and we can follow up there. Kevin, thank you so much for your time today.
Yeah, thank you for your time. Yeah.
All right. Thanks you all. Goodbye.